Hello everyone, welcome back to Electric Fields tutorial. Now today we are doing question 11, and the main concepts for question 11 that you need to know is that number one, there is no electric field inside a metal object if it's not connected to a source of EMF. Number two, for electric fields graphs, the sign convention indicates direction. So if it's positive, it might be, to the right or left, and negative, and so on and so forth. And number three, for the neutral point, there is zero electric field strength. So let's take a look at the question. There's two spheres, A and B, which are charged. And then the variation with the electric field strength with distance is shown in figure 11.2. Now, first of all, you see that there are two flat areas on the graph here where the electric field is zero. This is only possible if the two spheres A and B are conductors. All right. Now, next, you can see that near the sphere A, the electric field is strong and towards the positive direction. And for sphere B, the electric field is also strong and in the negative direction. This is the negative direction. Okay, Ken? Strong negative. Right. Um, and then you can notice that the electric field goes to zero here. So this is going to be a neutral point. And the neutral point, as you can see, is closer to the right, which means that actually sphere B has a smaller charge. Okay, so from this graph, we can already tell three things. Number one, the spheres are conductors. Number two, because there's a neutral point between the two spheres, they must be either both positive or both negative charges. Otherwise, the neutral point will be outside of the two spheres. And number three, because the neutral point is closer to sphere B, so sphere B has a smaller electric charge. So let's take a look at what is the evidence for the statement. The evidence for the statement that the spheres are conductor is that the graph shows electric field strength inside the spheres. Number part two, what is the evidence that the spheres are both positive or both negative? First of all, there is an electric field strength point zero in between the two spheres. Hence, the electric fields must be pointing in opposite direction. That means to say they're either both going in towards the neutral point and cancel out, or they're both going out of the neutral point and so they also cancel each other. Okay, so if one is positive and one is negative, then there cannot be a neutral point in between the two spheres. Now, let's take a look at part B. State the relationship between electric field strength and potential gradient at a point. Now, the electric field strength is numerically equal to the potential gradient at that point. Now, to explain what is meant by that the electric field is the potential gradient, let's take a look at these formulas over here. As you know, the four formulas inside this box is only true for point charges. However, the formulas outside the box are true for all charges. Now, how do we get from the bottom, which is the electric potential, to the top, which is the electric field strength? The formula for this will be the electric field strength is the negative of the change in the potential with distance. Sometimes we also write that the electric field strength is approximately equal to, okay, the magnitude of the delta V over delta R. Okay, so this is how we represent it. Now, if you go ahead and you differentiate the V with respect to R, you will get E above, okay, negative E. All right, so what does this mean actually physically? Now let's imagine this potato, which is positively charged, and we positively charge a potato to 400 volts. Now, if we draw the equipotential lines around the potato, you can see that there's 300 volts and there's 200 volts. Now, if you take a look at how the voltage changes with distance, over here it changes 100 volts, okay, in a very short distance. Now, and then over here, you can tell that over here there's a change of 100 volts in a long distance. So you can see that when the 100 volts changes over a short distance, the field here is a strong electric field, strong E field. And when the 100 volts changes over a longer distance, my gosh, what was that? The 100 volts changes over a long distance is a weak electric field. So basically, if there's a very big change in the potential or big potential difference in a short distance, then the electric field is very strong. Okay, so that's what's meant by potential gradient. Actually, is how much the potential changes with distance. So let's take a look. The relationship between electric field strength and potential gradient is numerically equal to the potential gradient at that point, or the negative of the potential gradient. Now, state and explain the distance x at which the rate of change of potential with distance. Rate of change of potential with distance, if we give it a Google Translate, if we Google Translate what is meant by rate of change of potential with distance, you just basically get dV/dr. And basically, rate of change of potential difference will be E field strength. Okay, so they are asking where is the rate of change of the E field strength, the maximum, where is the E field strength, the maximum and minimum. So let's take a look. Over here, this is the E field strength, which is also equals to the dV/dr. So basically, the dV/dr is maximum over here, max, and dV/dr is minimum over here, minimum. Okay, okay. So this is where the field is strongest, and that's where the field is weakest. So the field strength has a maximum value at x is 11.4 cm because that's where this part is, and the field strength is 0 at 7.9 cm. So once we Google translate what is meant by rate of change of potential with distance, we know that it's E field strength. So that's the end of question 11. Okay, let's take a look at question 12. In question 12, the key concepts are as follows. Number one, inside a metal conductor, which is not connected to a battery, the voltage is constant throughout the conductor. Number two, when you draw a potential graph, the steepness of the potential graph is the electric field strength. The gradient of the potential graph is the electric field strength. Number three, the equation V equals to 1 over 4 pi epsilon naught Q over R is only valid for a single point charge. So you can't use it to find the potentials near multiple charges. And finally, the last equation that we know is a golden equation for conservation of energy, KE1 plus EPE1 plus work done equals to K2 plus EPE2. So over here we have two metal spheres A and B and some point in the middle, and here's a graph of the potential with distance. So we can tell that both of the metal spheres are positively charged. How come? Because both of the metal spheres, one of them is charged to 835 volts, and then the other metal sphere is charged to, I think, around 389 volts or 390 volts. Okay, so basically what we have is that the sphere on the left will be charged to 835 volts, and then the sphere on the right is going to be charged to 390 volts. Now you can tell from here that the spheres have different charges on them, and it looks like if you can kind of like guesstimate, all right, that the neutral point will be somewhere on the right. So let's try to figure out where the neutral point is. So as you move towards the right, the voltage between the spheres will start to decrease until you get to the neutral point. And you can guess over here, this is the neutral point over here. Now, how do we know that this is the neutral point? Because you see, the gradient of the electric field, the gradient of the potential is 0. And so this is where the voltage does not change. And that means that that is where the electric field is 0. Okay, so now let's take a look at the question on the left. Now, state and explain the direction of the electric field at point P, where x is 25 cm. So this is 25 cm over here. Now, so in order to find the magnitude of the electric field, we will need to draw a tangent, but they didn't ask us to find the magnitude. Now, we know that since the voltage is decreasing to the right, that means the electric field will be pointing this way, E field. Okay? Now, so you take a look at the positive charges. over here, since this is a positive charge, the electric field will be coming out of the charge. Okay, okay. Sorry, the neutral point is there. So the electric field will be coming out of the charge this way. The electric field will be coming out of the charge this way. So uh, at around 25 cm distance, um, the electric field will be pointing in this direction to the right. So how do we explain it in physics? At x is 25 cm, the electric field is in the positive x direction. The direction of electric field always points from high potential to low potential. Alternatively, you can say that the gradient of the graph at 25 cm is negative, so the direction of electric field will be in a positive direction, since E is minus dV dx. Okay. Now determine the force on an electron placed at point P, where x is 35 cm. At x is 35 cm, that's the neutral point, because the potential gradient of the graph is zero, or the potential is horizontal. Hence, the electric field is zero, therefore there is no force on the electron. It is a neutral point. By making reference to electric fields, explain why potential is constant for distances between 0 and 9 cm. That means to say inside the metal sphere. Now, as we know, um, inside a metal sphere, there is no electric field. Okay, okay? So there is no electric field inside the metal sphere. So since there is no electric field inside the metal sphere, the potential must be constant. Because if the potential with distance graph is not constant, if there's a potential difference with distance, then there will be a E field to the right. If the potential is sloping this way instead, then there will be a E field to the left. But if the potential is constant with distance, then there will be no E field. Okay, so let's take a look inside here. Now let's take a look at the graph and find out where would there be E field and no E field. So we know that at the neutral point where the gradient is horizontal, there is no E field. This side, when the E field is sloping to the left, the E field is to the left. The potential is sloping to the left, so the E field is to the left. So over here, the potential is constant, so there is no E field. And over here, the potential is also constant, so there is no E field. All right. So the voltage change, the potential difference tells you that there will be a force on the charged particles which makes them move. That's why in a circuit, what makes electrons or the current move is a potential difference, not the potential itself. A student states that the potential decreases with distance x for distances between 10 and 25 cm according to the expression Vx is constant. Use data from figure 12.2 to show whether the student is correct. So basically what you need to do is to choose 2 points. Then after that, you multiply them and multiply them to see if it's constant. So you take 1 point over here, all right? Maybe you take this point. Okay, so you get like 15 and then 520. And then you take another point over here. Generally, I prefer to take points which are further apart because, less experimental error. So I take 10, 750, and over here, I'll probably take around maybe 20 and 400. Okay, 400. Then after that, I will multiply them together and show that they are not the same. So you can see at x equals to 15, V is 515. So 15 times 515, that is the constant, over 20 times 405. And you can see that these two are not equal to each other, not constant. Okay, now where does this equation come from? Why is Vx equals to constant? You mean voltage times distance will be a constant? The student is thinking of this equation, 1 over 4 pi epsilon naught q over x. Now, if you do that, then you get Vx is equals to 1 over 4 pi epsilon naught q, which is supposed to be a constant because the charge is a constant. So why is the Vx not constant? It means that this equation does not apply. Does not apply here. Why does this equation not apply here because this equation is only valid for a single charge. The student's expression is meant for potential due to a single charge. V is equals to 1 over 4 pi epsilon naught Q over X is only for single charge. And figure 12.2 is the combination of both charges potential adding up. All right, so it's not possible. So what is the figure 12.2 formula instead? The figure 12.2 formula, okay, will be V is equals to 1 over 4 pi epsilon naught Q1 over X plus 1 over 4 pi epsilon naught Q2 over X 50 minus X. I think because the charges are half a meter apart. So actually, this is the formula of the graph, not a single charge. Okay, let's move on. An electron initially at rest a long distance from the spheres approaches the spheres and passes between the 2 points. Calculate the minimum speed of the electron as it crosses the line joining the centers of the 2 spheres. Now, let's take a look at how the electron can pass through these 2 points. Okay, so over here, let's take a look around this point. If you see on the graph, the voltage is 750 volts plus 750 volts. Okay, near the middle, the voltage is around 295 volts. Okay, so this is the neutral point. Over here, the minimum voltage is plus 295 volts. And then near to sphere B, the voltage is probably, let's say the voltage here is around 350 volts. Okay, 350 volts. So over here is plus 350 volts. Now, let's say that I have a charge, which is an electron, minus 1e, and then this charge is very far away. And not only is it very far away, it's stopped very far away. So if it's very far away, the initial EPE1 will be 0. And it's stopped, so the KE1 is also 0. Now, because the 2 spheres are positively charged, the electron is going to be attracted towards the 2 spheres. So let's say it reaches this point. When it reaches this point, it will be a minus 1e charge at plus 750 volts. So if you think about it, the EPE at this point will be QV, which is minus 750 E. Okay, so this is the EPE at this point is minus 750 E. So let's take a look. So in this case, if it reaches at this point, what will be the KE? The kinetic energy will be plus 750 E. Right. Now, those of you who are confused, E is just the electric charge of a electron, which is 1.6 times 10 to the power of minus 19. So if the electron goes to this path, it loses 750 E joules of PE, and then it gains 750 E joules of KE. Now, what if it goes this way? All right, if it goes this way, it gains 350 E joules of KE. And what if it goes this way? This way it gains 295 E joules of KE. So which route allows it to gain the least kinetic energy? The route that allows it to gain the least kinetic energy will be the route that passes through the neutral point, least KE gain. Okay, so if you take a look, that kind of makes sense because let's say if this is a positive charge here and this is an electron and the electron passes close to the positive charge, I will expect it to go very fast. But if the electron is passing far from the electric charge, not as fast, right? Because I would assume that as it goes towards the charge, it gets faster and faster. But if it's just going away from the charge or around the charge, it will not go that fast. Okay, so basically, the moral story is, okay, for the electron to gain the least KE, it must pass not so close to the 2 charges. And what does it mean by not so close to the 2 charges? Well, the place that is electrically equidistant from the 2 charges electrically is the neutral point. So if it passes through the neutral point, that is where it will gain the least kinetic energy. Okay, so let's take a look. As it crosses the line joining the centers of the two spheres, the minimum point at which it will get um, the least KE gain will be at the 295 volt point, neutral point. Okay, so let's take a look at the suggested answer. So KE at long distance away, 0 KE and 0 EPE. That means KE1 is 0 and EPE1 is equal to 0. So when it comes towards the two spheres, basically what happens is that the charge multiplied by the voltage will be equals to the kinetic energy. Okay? The charge here being negative, minus 1.6 times 10 to the power minus 19, and then the voltage that they chose is 295. So this will be the minimum kinetic energy. Where do we get these values from? Over here, this is the mass of electron. You can get it from your lecture notes. Over here, this of course is the charge of the electron. Okay, which we already know is negative 1.6 times 10 to the minus 19. Right, so once again, when it's far away, EPE is 0, K is 0. When it reaches that point, the EPE will be QV. And when it reaches a plus 750 volt line, then the EPE will be negative 750 volt. That means it loses 750 E-joules, and then it gains 750 E-joules of KE. So where will it gain the least KE? It will gain the least KE if it passes to the point with the lowest positive voltage. Okay, now describe the path of the electron for the minimum speed. At a long distance away, the electron has 0 KE and 0 EPE. The electron has to pass through the point where the potential between the spheres is at a minimum. Okay, so basically it will pass through the line joining the two spheres at the neutral point. Okay, now after the electron passes through the minimum point, where do you think it will go? So this is the electron moving. Okay, so it passes through this neutral point. It won't stop there, you know. The electron has a lot of kinetic energy now. So now the kinetic energy of the electron will be 295 E joules of Ke. Now, so it will actually proceed out all the way until infinity again, where the Ke will be equals to 0 and EPE equals to 0. So the electron will pass through the line joining the two spheres. Thereafter, the electron will continue on to infinity, where it reaches 0 KE. Okay, can? So at a long distance away, 0 KE, 0 EPE, it will pass through the line joining the two spheres at the neutral point at x35 cm, and thereafter the electron will continue outwards, where it will reach infinity again with 0 KE, and then it will come back. Okay, and this is question 12. Okay, let's take a look at question 13. Uh, and question 13 is about motion of a charged particle in a uniform electric field. Now, please note that in a uniform electric field, the four equations that are in the center of the circle over here, they don't apply. They don't apply because these equations only apply for point charge fields. So what equations do apply? F equals to EQ, U equals to QV, and E equals to dV/dr. These are the equations that do apply. These equations do apply. Okay, so there are only three equations you can use for uniform electric fields. F equals EQ, E equals to dV/dr, and U equals to QV. The rest inside the circle cannot apply to uniform fields because they are only for point charges. So here's an electron moving with speed 1.5 times 10 to the power 7. The charge, of course, is minus 1.6 times 10 to the power minus 19 coulomb. We use the magnitude of this charge, okay, because we know which way the electron will deflect. As it goes into the plates, it will deflect upwards in parabolic motion. And then after that, it will go straight. Down here will be straight, and down here will be deflect upwards. Okay, deflect upwards. So These plates are 60 mm long and 20 mm apart. The upper plate is at a higher potential between the lower plate, and the electric field strength between the plates is 4,000 newtons per coulomb. Now, first of all, I want to go through with you the Subatsu method of solving parabolic motion in case some of you have forgotten. All right, so this is the acceleration A. Let's say the A is upwards, okay, and this is the initial velocity U, okay, and then the start point of the motion will be 0, 0, okay, and the end point of the motion will be X and Y. Okay, X and Y. So how do we measure X and Y? Basically, this point, imagine that there's a giant graph paper over here. This is X and this is Y. So there is some value of X and Y displacement up here. Now, how do we do the Subatsu? Let me give you some examples. So assuming that A is 10 and the U is 15, okay, and then over here is 80. All right, so we'll fill in first Suvatsu. Now, the first five elements are all vertical elements, and then the last two elements are horizontal elements. Now, let's take a look at what we can fill in first. The acceleration, we normally fill in acceleration first. Acceleration will be 10. Because it's upwards, it's plus 10. The initial velocity is in the horizontal direction, so its initial velocity will be 15. So what about the displacement? The displacement horizontally at the end, x displacement is 80. So we write down 80. Then what about the y displacement? We don't know what the y displacement is, it's unknown. What about the y velocity? Now you see the initial velocity is horizontal. So the initial vertical velocity will be 0. Okay, Ken? So what is the strategy for the left-hand side and the right-hand side? The left-hand side has got four equations. S equals to ut plus half at squared. S equals to half u plus vt. V is equals to u plus at. And the last equation is v squared equals to u squared plus 2as. For the right-hand side, there's only one equation. S is equals to ut. So using this, we are able to find out, first of all, what is the time. So the time will be equals to S over U, which will be 80 divided by 15. Okay, so just doing a calculation quickly, 80 divided by 15 gives you 5.3 seconds. So this will be 5.3 seconds. So now we have the time, so we can fill in the rest of the y equations over here. So we can use s equals to ut plus half at squared. Using the values from the left-hand side, we can get y is equals to 0 plus half 10 5.3 squared. All right, so this is how you get. So y is equals to 5 times 5.3 squared, which will give you about 140.5, okay, value. So this is how you use Suvatsu. Now we can apply this also to electric fields. Okay. Now, so what we'll do is that we will use the Suvatsu method and slowly write up the values. So here is Suvatsu. Okay. The what we can write first of all is the speed of the horizontal motion of the electron, 1.5 times 10 to the power of 7. Then we can write the horizontal displacement of the electron. The horizontal displacement of the electron is 60 mm. So that's 60 times 10 to the power minus 3. Now let's take a look at 20 mm. 20 mm is not equals to the vertical displacement. We don't know where the vertical displacement is because the vertical displacement, the electron might not have touched the plate yet, or it have even gone past the plate. Okay, so we don't know what's the value of y. So put the value of y as just y. Then after that, what is the initial vertical velocity? The initial vertical velocity is 0 because the electron is only moving horizontally. Now that leaves us the acceleration of the electron left. Now for this one, the last concept we need to know for today is that the acceleration of the particle is A is equals to F over m. So A is equals to F divided by m. But what is F? For a charge, F is equals to EQ, right? But what is E? Okay, well, E, they've given us in the question is 4,000. So this 4,000 multiplied by 1.6 times 10 to the power of minus 19. Notice that I use the magnitude. because the direction of the deflection I already know is upwards due to common sense. Okay, then divide it by the mass of the electron, which is 9.11 times 10 to the power of minus 31. Okay, so the acceleration of the electron will be 7.03 times 10 to the power of 14 in a vertical direction upwards. All right, so now we are ready to answer the question because we've got every data that we need already. What is the time taken by the electron to exit the parallel plates? We can see that the time taken by electron to exit the parallel plates is a horizontal problem because there are two horizontal variables. So the time taken for the electron to escape the horizontal plates will be Sx divided by Ux, which will be 60 times 10 to the power minus 3 divided by 1.5 times 10 to the power of 7. So this will be 4 times 10 to the power of minus 9 seconds. So we can put in here t is equals to 4 times 10 to the power of minus 9. Now calculate the magnitude of acceleration between the plates. We've already done that. Okay. Hence calculate the angle through which the electron beam will be deflected. So basically what they're asking us to find is what is the final velocity at the end. So we use the equation v is equals to u plus at in the vertical direction. Okay, can. So we write Vy is equals to 0 plus 7.03 times 10 to the power of 14 multiplied by 4 times 10 to the power minus 9. So the vertical velocity will be 2.81 times 10 to the power of 6. Now, so at the end of the motion, the electron will be going in this direction. This will be Vx and this will be Vy. Now the Vx we know from previously the Vx value is 1.5 times 10 to the power of 7. And the Vy value we have just worked out is 2.81 times 10 to the power of 6. So the resultant velocity Vr angle will be over here. The angle of the motion will be the arctangent of the Vy over Vx. Okay, so the arctangent of Vy over Vx will be 10.6 degrees. So basically, the electron is going to go into the plates and deflect upwards. It's going to pick up a vertical velocity, and because of that, there will be an angle that is deflected. All right, so this is a key problem type for electric fields, which is the deflection due to an electron inside the parallel plates. And that is all for question 13. Now let's take a look at question 14. Once again, question 14 is about parabolic or projectile motion. Uh, and in between the plates as the object undergoes projectile motion, okay, it will actually form a parabolic path. Now I need you to memorize the definition for projectile motion. Projectile motion is a motion where there is a constant velocity in one direction and a constant acceleration in a perpendicular direction. Okay, so basically, the horizontal velocity is constant, and the perpendicular acceleration is also constant. So sometimes we say uniform acceleration in a perpendicular direction. Okay, so how does this setup ensure that all the electrons emerging from B have the same speed? So over here we have a hole, and over here we have another hole. Okay, now if the electrons are moving too fast, they will go here, and then they will hit the plate. And then if the electrons are going too slow, they will go here, and then they will hit the plate. So only if the electrons have the correct speed, they will exit through the plate. So after the electrons enter the electric field, they will experience a downwards electric force because the bottom plate is positively charged compared to the top plate. And given that the initial angle is fixed and acceleration is constant, the exact path followed by each electron depends on the initial speed. So if the electron is too fast, they will travel beyond the hole, and if the electron is too slow, they will travel short of the hole. Okay, so electrons with higher speed will travel further than B. Electrons with lower speed will strike the plates at less far than B. So this is how they ensure that all the electrons coming out have the same speed. So determine the magnitude and direction of the acceleration of the electron while it's between the plates. Now the formula to use for this is E is equals to V over D. Now this comes from the equation E equals to minus dV dr, which says that basically the electric field strength is the potential difference divided by the distance between the plates. Okay, or basically equals to the potential gradient. Okay, so in this case, the electric field strength, there's a 45 volts difference, and then there's a 0.006 meters separation between the plates, giving you an electric field strength of 7,500 newtons per coulomb. So the force of the electron, the acceleration of the electron will be force divided by mass, and force is equals to EQ. Remember that only F equals to EQ can be used for parallel plates. The other equations in the center of the circle only apply to point charges and cannot be used. So that will be 7500 times 1.6 times 10 to the power minus 19 divided by the mass of the electron, which is 9.11 times 10 to the power minus 31. So the acceleration will be 1.32 times 10 to the power 15 in a downwards direction. Okay, so this is how you do part B. Calculate the speed of electrons emerging from slit B. There are two ways to do this. The first way to do this will be the Suvatsu method. Okay, yeah. So the Suvatsu method will be as follows: Sy, Uy, Vy, Ay, T, Sx, Ux. So fill in all the values that you have. Okay, so the electrons are moving um at what speed? Okay, the speed's not given. Okay, so it's 25 mm. Okay, so what we're going to do is that we're going to fill in all the values for the projectile motion. Okay, the initial angle is 15 degrees. The plates are 25 mm apart, so it's 0.025 meters. Okay, and the acceleration was given just now as 1.32 times 10 to the power of minus 15. Oh, sorry, 10 to the power of 15. Okay, so let's fill in the values first. Now, if we take the start point to be 0, 0, then the ending point here, the coordinate will be 0.025 and 0. So over here, we can fill in the values for Sx 0.025 and Sy will be 0. Now, we don't know what is the initial vertical velocity, will be u sine 15. And we don't know what is our initial horizontal velocity, that will be u cos 15. But we do know the acceleration is 1.32 times 10 to the power of 15 in a downwards direction. So we put minus 1.32 times 10 to the power of 15. Now, let's take a look at how we can solve this equation. It looks like it's going to be a simultaneous equation with both u and t as unknown variables. Okay, so let's write the right-hand side equation first. So we get Sx is equals to uxt. So if you fill in the value 0.025 is equals to u cosine 15 multiplied by t. Okay, now let's write the second equation, which is the equation on the left. Okay, and we can write Sy is equals to uyt plus half ayt squared. So let's fill in the values. 0 is equals to u sine 15t, okay, minus, okay, so we work out this ay first. 6.6 times 10 to the power of 14 t squared. Okay, so it looks like the easiest way to do this would be to substitute out um, u, I guess. I guess we can substitute out u. Okay, so or we can substitute out t. So u is equals to 0.025 over t cos 15. Okay, so let's put this inside here. So 0 is equals to 0.025 over t cos 15 times sine 15 times t minus 6.6 times 10 to the power of 14 t squared. Okay, so the t's cancel out and then sine over 15. So 0.025 tangent 15 minus 6.6 times 10 to the power of 14 t squared is equals to 0. So from here, I guess we can solve for t. T is equals to 3.19 times 10 to the power of minus 9 seconds. Well, okay, so since we've substituted that inside here, I guess we can reverse substitute t into here, and then we can get 0.025 is equals to u cos 15 multiplied by 3.19 times 10 to the power of minus 9. So that gives us u equals to 8.12 times 10 to the power of 6 meters per second. Okay, so right, so we got the initial velocity, yeah? Calculate the speed of electrons emerging from slit B. Okay, so now we have got the initial velocity of electron is 8.12 times 10 to the power of 6. But one property of projectile motion is that the starting speed and ending speed, if they are of the same height, will be the same. This is also 8.12 times 10 to the power of 6 meters per second. Due to conservation of energy, what goes up must come down, and it goes up at the same speed, it will come down at the same speed, so long as it's at the same level, okay, in terms of energy, potential energy level. Okay, so the final answer will be 8.12 times 10 to the power of 6. Now, the answer scheme shows an alternative way of doing it, which is to substitute out for time first, okay, so that you get u. Um, that's also an equally valid method, right? And that's the end of this question. Okay, let's take a look at question 15. A small positive charge placed at point L inside a uniform electric field experiences a force of magnitude F. Okay, so let's take a look. Now, once we show these electric field lines, okay, the first thing that you want to do is to draw the source of the electric field. So, knowing that these lines are horizontal and uniform, we can tell that the source of electric field is going to be parallel plates, where there's a positive plate on this end and a negative plate on this end. Now, so if you place a positive charge at point L, definitely there's going to be a repulsive force in this direction. Not only that, the electric potential energy will look like this. This will be high EPE and this will be low EPE. Now, how do we know that? Because if we let go of the positive charge, it is going to dash across, okay? It's going to go pew away from the positive plate. So because it goes pew away from the positive plate, the place where it starts off will be high EPE, and the place that it's going towards will be low EPE. So when the charge is moved from point L to point M, the potential energy of the charge will be lower. So it will be a loss, okay, loss. Okay, next. What is the other method that we need to use to actually determine how much is gained and how much is lost? Well, you see, the horizontal movement of the electric charge has no change in EPE because, frankly speaking, the EPE is perpendicular to the electric field. So if you move along the EPE line, there's no change in EPE. It's only when you move from a high EPE line to a low EPE line, then there'll be a change in EPE. So the perpendicular distance of y squared does not matter. Does not matter. So there will only be a x component. Okay, x component. Now, the third one is yfx. Remember that the work done is equals to force times distance. Force times distance. So what about the work done by the electric force? The work done by electric force will be the electric force multiplied by the distance. Now in this case, which way is the electric force pointing? On the positive charge, because there's a positive plate here, the electric force is pointing in this direction. So no matter what way you move, okay, it will be the electric force multiplied by the distance moved or the displacement in the direction of the force. So it doesn't matter how you move, you can even go backwards if you want. Okay, you can even go backwards behind the plate, around the plate, and then end up at this point. But D is your displacement, okay, from the start point to the end point. The work done will be the electric force multiplied by the displacement in the direction of the force. Okay, okay? So the EPE will be lost. The EPE will be lost due to work done by electric force, and the amount of EPE loss will be the force times the displacement x. So that's question 15. Let's move on to question 16. Now, in question 16, I want you to imagine there's a plate here, okay? And then this is a horizontal plate. So there is a positively charged particle P. Now, if there is no voltage, what will happen to P is that it will fall down because it is has a weight. Okay, so it will fall this way, fall down. But when there is a voltage, so what happens is that we power up the voltage over here. So now we have a voltage. Now, because of the electric repulsion, there will be a repelling force. Okay, and then this force will be EQ. And then now, if EQ is equals to mg, then the P will float. Okay, it will float in equilibrium, or it will move at constant velocity. Okay, let's take a look. So now, if the voltage is increased, P rises, and if the voltage is decreased, P falls. Well, that kind of makes sense because if there's no voltage, then P will fall. So if there's more voltage, then P will rise. Okay, now let's take a look at where the EPE is stronger or where the EPE and GPE is weaker. So let's take a look at a case where there is no voltage. No voltage. When there's no voltage, point P will tend to fall downwards. That means this point will be high GPE and this point will be low GPE. Does that make sense? Because when you let go and it pew downwards, that means to say the top part will be high GPE and the bottom point will be low GPE. What about when there is strong voltage? So let's say we have a very strong voltage over here. Okay, so it's very, very positively charged. So then the electric force of repulsion will be high, electric force will be high, and the weight will be relatively smaller. So it will tend to move upwards. So if it moves upwards, this place must be high EPE, and this place must be low EPE. So as you can see, right, the EPE and GPE positions are opposite. Over here will be GPE high, GPE low. Over here will be EPE high, and over here will be EPE low. Now, let's take a look at which plate is correct. So if you decrease the V, when you decrease the V, it will fall. When it fall, GPE will be lower, but EPE will be higher. So it decreases both the GPE and EPE is not correct. Decreasing V will fall, increases the EPE, and decreases the GPE. That's correct. Now, we should always check the other answers to see if our reasoning is wrong. Increasing V, when you increase V, it will rise. When the object rises, the GPE will be higher and the EPE will be lower because of, GPE high is up there and EP low is up there. So increases both, that's wrong. Okay, the change of electric potential energy of the particle must equal the change of the GPE of the particle. Well, this is only assuming that there is no air resistance. Okay, so that's not always the case. All right. Um, Now remember the energy equation will be KE1 plus EPE1 plus GPE1 plus the work done equals to KE2 plus EPE2 plus GPE2. Now you can see that there are other terms inside this equation. So it doesn't mean that EPE and GPE will convert to each other because they can also convert uh, to work done by external, so for example air resistance, or KE. So for example it speeds up. Okay, if it speeds up, then the EPE and GPE will not be the same value. Okay, so the answer should be B. Let's take a look. When V is decreased, P falls to a lower position, hence GP decreases. Yep. Okay, so the lower plate is at a high potential. So as charge move out down, EPE increases. The option D is not correct because the KE of the particles can also change. So the loss in GPE or EPE may not be equal to each other, especially if there is air resistance or if there is a change in KE. Okay, so this is the end of question 14. And now we've come to the end uh, of the tutorial.